It's a great pleasure to deliver a tutorial on nonlinear optics in fibers and waveguides, and I'd like to begin by thanking the organisers and chairs for giving me this opportunity. I also wish to thank the many students, postdocs and other collaborators with whom I've worked over the years and who have all helped me understand the sometimes rather subtle aspects of this field. There are many topics to cover in a tutorial on this subject, and it's not possible to be both exhaustive and accessible, so I'm focusing around half the talk on a broad overview and then to review recent results and current directions. I'm including results from many other groups as well, and I'd like to thank contributors for providing me with material and slides. Nonlinear optics wouldn't exist as a field without the invention of the laser, and it's appropriate to recognize the importance of the laser, especially this week, because it was 60 years ago this coming Saturday, on the 16th of May 1960, that laser operation was first observed by Ted Mayman. The importance of the laser, both to science and society, has now been recognized by the United Nations with the proclamation of the 16th of May as the annual International Day of Light. And I'd encourage you to look at the many specific events planned this year online to celebrate this 60th anniversary, including here at Clio in a special symposium involving Professors Yariv and Capasso. A year after the invention of the laser, the first experiments in nonlinear optics were performed. There are two interesting things about this paper. The first is that they mentioned they use a commercially available laser, indicating that within 12 months of the first fundamental demonstration, a laser market was already established. The second is that the experimental evidence for the second harmonic, which should be a low contrast spot indicated by the arrow and within the red circle, was actually removed during the typesetting of the paper. So strictly speaking, the first paper on nonlinear optics didn't really include the evidence for it. We'll be talking a lot later about soliton effects, and it's interesting to note that their first study also dates back to the 1960s. Through theoretical work in Russia, as well as work in the United States led by Charles Townes, where he was trying to explain experimental observation of extended damage tracks in glass. He realized that this implied that light was not diffracting beyond the point of focus, and this led him to develop a nonlinear propagation equation, and also on physical grounds to derive the hyperbolic secant solution for the trapped profile, well before the invention of the mathematical technique of inverse scattering in 1972. As well as leading to fundamental advances in nonlinear optics, the development of the laser immediately motivated the search for many new applications. One of the most important was the 1966 pioneering work of Charles Kao, who demonstrated the potential of optical fiber guidance for communications. Although Kao's interest was very much on linear distortion-free propagation, it wasn't long before the study of nonlinear effects in optical fiber became a major area of research. These are some of the milestones in the field, and perhaps we can identify the origin of the area of research as a distinct field back to the first edition of Agrawal's book on nonlinear fiber optics in 1989. I should add here that this is incomplete. Many of the important contributors are no doubt missing, and this list of dates really only includes those relating to silica fiber and not optical amplification or others. I'm now going to start to describe some of the basic principles of nonlinear propagation in waveguides, and perhaps the best starting point is to realize that a waveguide's guidance properties depend on both material and structural characteristics. Linear dispersion depends on material and waveguide contributions, and the nonlinear response depends on the intrinsic nonlinearity of the material plus the degree of mode confinement. Now, A talk on materials would be a tutorial of its own, but what I would like to stress is that for all workers in this field, it's essential to keep track of the evolution in the use and availability of new materials as they start to be applied. There are regularly review papers in this area, and it's something that one really must try to keep track of as much as possible. In order to understand nonlinear optics in fibers and waveguides, one needs to have some kind of propagation model, either to develop the theory or to interpret experiments. In all cases, we start with Maxwell's equations and we derive a wave equation, and in this case we include both linear and nonlinear polarization terms. If we consider the simplest case of a scalar approximation, the electric field is then written in terms of different components. We're particularly interested in the temporal envelope AZ of t and its frequency domain equivalent, which gives the spectral amplitude. Now, of particular interest in this slide is the expression of the linear propagation constant beta of omega in a Taylor series with different orders and different coefficients, and the expression for the nonlinear perturbation to the propagation constant in terms of a nonlinear refractive index N2, which will become very important later in the definition of a nonlinear coefficient for fiber propagation. Although the field is nonlinear fiber optics, it's always interesting to remark that it's the linear dispersion that actually determines the qualitative regime of propagation. In particular, we generally distinguish propagation regimes by the sign of the second order group velocity dispersion, or GVD beta 2, as it's this that determines whether the dynamics are focusing or defocusing in a temporal sense. The GVD is often expressed with two definitions, either beta 2 itself in picoseconds squared per meter or per kilometer, or a D parameter expressed in picoseconds per nanometer per kilometer. Since this is a tutorial, it's worthwhile stressing that both units of course describe the same physics. In fact, they both quantify the temporal walk-off of two pulses with different wavelengths over a different distance in a fiber. It's just that the parameter D gives this walk-off as picosecond per nanometer per kilometer, while beta 2 gives the walk-off in terms of an angular frequency difference between the two wavelengths, that is picoseconds per 2 pi terahertz per kilometer. But it's exactly the same thing. This is a very useful figure to illustrate how the interaction between nonlinearity and dispersion can yield qualitatively very different dynamics depending on the position of the pump wavelength relative to the fiber zero dispersion wavelength. The figure is certainly an oversimplification, but it allows us to see how, depending on whether the group velocity dispersion is anomalous, beta 2 negative, or normal, beta 2 positive, we can see a variety of different effects that can take place. Now, it's precisely because there are so many of these different effects that it sometimes makes interpreting physics based on experiment only very difficult. And it's for this reason that we very often find in nonlinear fiber optics and in nonlinear waveguide optics in general that experiments are always accompanied by parallel numerical modeling. The dispersion of an optical waveguide depends both on its material and its structure, and engineering the dispersion of fiber to some degree has been possible since the very early days of fiber optics by appropriate design and doping of the core and cladding. A lot of work here focused on telecommunications applications around 1550 nanometers, where many different designs were developed, such as dispersion flattened or dispersion shifted fibers for specific applications. From the perspective of nonlinear fiber optics, the real revolution in the field of fiber dispersion engineering occurred in the 1990s following Philip Russell's idea for a single material fiber containing a photonic bandgap microstructure. Actually, his original proposal for this was written down and noted during a CLIO conference in 1991. And although his initial thought was focused on fibers that guided through a photonic bandgap effect, it was soon realized that the microstructure cladding concept also provided tremendous flexibility to engineer the effective core cladding refractive index difference, even when fibers guided in a more conventional way through some kind of modified total internal reflection. It took a few years before the analytical concepts and the computational tools became available to design photonic crystal fibers conveniently, but once they did, it was soon realized that there was remarkable control over the dispersion properties of even simple structures like a pure silica fiber with air holes surrounding a solid core in a hexagonal arrangement. It became possible to shift the zero dispersion wavelength from the intrinsic material wavelength of 1.3 microns in silica to much shorter wavelengths, and even with certain designs to create fibers with multiple zero dispersion wavelengths. And moreover, this coincided with a wider realization a little later that dispersion engineering in other classes of waveguide had perhaps been overlooked for applications in nonlinear optics. And this motivated a subsequent tremendous effort to study similar dispersion engineering in other platforms and materials. An excellent review of the early work is given in this 2008 paper. For the particular case of optical fiber, this 2017 review provides a very comprehensive summary of the different fibers that are available and how they're being combined with different materials to create a new class of hybrid fiber, where by combining waveguide engineering with targeted material properties, completely new and unexpected functionalities are being obtained. There's a lot of fundamental research as well as application-oriented research going on in this field, and this review provides a very nice starting point if you're unfamiliar with the many developments that have taken place recently. Now, before we move off the topic of fiber structure, there's one final important point I'd like to make, and this is that we need to consider very carefully the particular mechanisms of guidance used for a particular structure, because they can vary significantly. The very first microstructured or photonic crystal fiber were distinguished into essentially only two classes: solid core fiber that guided via some form of modified total internal reflection, and hollow core fiber that guided over a narrow frequency range through a photonic bandgap effect. But other hollow core fiber structures have now been developed that exhibit broad band guidance, and the mechanism here is different. It's best considered in terms of some kind of anti-resonant model where a central hole is surrounded by a glass structure that's anti-resonant, leading to enhanced reflection of light back into the core. Now, there are different ways and terminology and formalism describing this particular mechanism in detail, and the 2017 review paper that I mentioned before is a great place to start to become familiar with the different concepts, models, and vocabulary used. We now move on to the more formal description of nonlinearity in fibers, which is commonly introduced via a nonlinear polarization term in the wave equation. This is written in terms of an instantaneous Kerr term and a delayed inelastic Raman term, with the parameter Fr here describing the fractional contribution of the Raman effect to the overall nonlinearity. The particular physics of the Kerr term is usually interpreted as an intensity-dependent contribution to the refractive index via a parameter N2. In waveguides, we usually combine the nonlinear refractive index N2 with the modal effective area, which determines the confinement into a single parameter, gamma, and it's the gamma parameter which will subsequently appear along with beta 2 in the nonlinear Schrödinger equation. With the parameters of dispersion and nonlinearity now discussed and defined, we can write down the nonlinear Schrödinger equation, or NLSE. This is derived from Maxwell's equations via a wave equation and a number of approximations. And in particular, if we neglect the Raman effect for the moment, we can illustrate quite clearly the two key effects that occur when a high power pulse will propagate in a fibre. Note that I'm mentioning fibre propagation, but the NLSE also applies to many other nonlinear waveguides. On the bottom left, we illustrate the effect of linear group velocity dispersion. This will, acting alone, alter the temporal pulse shape of a pulse injected in a fibre without changing the spectrum. It's a purely linear process. On the right, we illustrate the effect of nonlinear self-phase modulation, which will broaden the spectrum, introduce spectral modulation, whilst leaving the temporal intensity unchanged. Both GVD and SPM introduce changes to the phase of the pulse with propagation, and the phase changes that are introduced have opposite signs, and under certain conditions they can balance exactly. When the effects of nonlinearity and dispersion do compensate, we obtain the formation of a stable or stationary fundamental optical soliton. Now, you can describe the effects of dispersion and nonlinearity acting on their own in terms of characteristic length scales. A dispersive length depending on pulse duration and dispersion, and a nonlinear length depending on the nonlinear coefficient gamma and the peak power of the injected field. When these two characteristic length scales are equal, we obtain a condition relating the fibre parameters, the power and the pulse duration, and if this is satisfied, we obtain the fundamental hyperbolic secant soliton solution. As well as the stationary fundamental soliton, periodic or higher order soliton solutions also exist within the NLSE framework. And these are defined in terms of the soliton order n, which is the square root of the ratio of these two characteristic dispersion and nonlinear length scales. Now, note here that it's very important to realize that the soliton order n is not a property of the input pulse. It's a general dimensionless constant of the system. It combines together both the power and the temporal width of the input pulse, as well as the dispersion and nonlinear parameters of the waveguide. Ideal higher order soliton propagation is periodic. It reproduces itself after a characteristic soliton period or soliton length scale defined in the bottom as Z sol. It's certainly possible to perform experiments in nonlinear fibre optics well described by a simple NLSE formalism as we've just seen. But in general, other nonlinear effects must also be considered. I mentioned before the Raman term. This is only one of two inelastic scattering effects that can generate new frequencies through interactions between an incident field and vibrational modes of the waveguide. Considering Raman first, in silica, this leads to gain at 13 terahertz from a pump, and it can be applied as a very versatile optical amplifier, and it is also seen in broadband spectral generation. For long pulses injected in the fibre, this can lead to spontaneous sidebands appearing around a pump, and for short pulses and solitons, it can lead to a continuous frequency shift towards longer wavelengths. A second and increasingly important nonlinear effect is Brillouin scattering. This is associated with much smaller frequency shifts when compared to the Raman effect, but it's being increasingly exploited in technologies such as sensors and on chip-scale platforms. Reviewing the many potential applications of gluon scattering in integrated photonics would be a talk of its own, but I'd like to refer you to this particular review article published last year, which provides an excellent survey of the state of the art, and I'd also recommend that you browse through the program of this conference to get an overview of other applications and fundamental studies in this field. We have now really covered all the basics we need and can begin to explore some applications. I'll actually begin with probably the most complex, that of femtosecond pulse pumped supercontinuum generation, as it was its observation in 1999 that really showed how the combination of short pulses and waveguides with the appropriate dispersion could lead to dramatic nonlinear effects, resulting, of course, in the particular application to frequency comb stabilization and the 2005 Nobel Prize. Now, the inset here shows the first supercontinuum spectrum reported in photonic crystal fiber, and this was really a remarkable result, generating such broadband light from the visible right out to the infrared with a readily available femtosecond source and one fiber. At this point, I'd just like to refer briefly to a chapter in a book I had the opportunity to edit with Roy Taylor a few years ago. This chapter was written by Janendra Ranker, who was at the time the postdoc who performed the first 1999 experiments on the supercontinuum. His words are really worth reading in full, but here are a few extracts where he highlights the importance of being curious, the role of luck, but luck coupled with hard work, and overall the importance of being supported to have a long-term outlook in one's research. As a result of these experiments 20 years ago, the supercontinuum has been extensively studied and is now a widely used and applied light source. It's industrially available, capable of generating light from the ultraviolet to the infrared well beyond 10 microns. Now, this particular picture, which shows spectral density obtained over particular wavelength ranges for particular pump wavelengths, which are shown as the circles, essentially becomes out of date every time I draw it. But it highlights the general aims of research in this area, both to extend wavelength coverage as well as spectral density. Now, filling in the gaps in any particular empty area of this graph requires a great deal of work, and in particular it requires an understanding of the dynamics that drive the supercontinuum process. So this is what we're going to look at now. Now, to understand how the supercontinuum is generated in detail, we need to go beyond the simple nonlinear Schrödinger equation and include other physics such as Raman scattering and self-steepening. Now, for background, you can see Agrawal's book as well as the other papers given below. And although the details can be complex in general, the basic idea is relatively simple to explain in terms of four main points. In particular, for the common case where we pump in the anomalous dispersion regime, the input pulse can be considered as a higher order soliton, which we'd expect to show periodic spectral and temporal evolution as shown. However, the effect of perturbations is to break this periodicity, and after initial temporal compression and spectral expansion, we see the breakup of the incident pulse into a number of distinct fundamental soliton components in the time domain, and this is associated with a complementary complex evolution in the frequency domain. Two aspects of soliton dynamics broaden the spectrum. There's dispersive wave generation to induce shorter wavelengths, and the Raman-Soliton shift to generate longer wavelengths. Now, things can get even more complicated than this, but that relatively simple picture allows you to understand and interpret a lot of the supercontinuum literature. At this point, I'd like to stress that many aspects of these dynamics have been known for some time. For example, the initial phase of propagation, spectral expansion and temporal compression, was referred to as soliton effect compression in the 1980s and used to generate short pulses. But continuing to revisit apparently well-known effects is important because we can sometimes find new ways to interpret old results. And for this case, we've been involved in recent studies showing how the central region of the compressed pulse can actually be described analytically in terms of a solution to the NLSE known as the peregrine soliton, a simple rational function. Details of theory, experiments and simulations are to be found in the paper shown here. It's worthwhile here to say a bit more about the process of dispersive wave radiation as well. Its physical origin can be derived from soliton perturbation theory and associated with the transfer of energy from a soliton in the anomalous dispersion regime to a phase-matched frequency in the normal dispersion regime. But this process can also be described in the frequency domain in terms of cascaded four-wave mixing between different frequency components under the soliton spectrum. This cascaded wave matching picture is complementary to the soliton perturbation picture, and it stresses that sometimes looking at the same phenomenon from different viewpoints can provide additional insight. And before we leave the topic of dispersive waves, I'd just like to briefly cite the extensive literature on dual dispersive wave generation in fibres, where a region of anomalous dispersion exists between two regions of normal dispersion. In this case, a soliton injected between these two zero dispersion wavelengths can generate two dispersive waves. And if this is done in a way where the position of the zero dispersion wavelengths actually vary with propagation, by having a dispersion decreasing fibre, for example, one can generate spectra that have a remarkably uniform profile, as shown on the bottom right. This dual dispersive wave generation and its application to broadband supercontinuum generation was extensively studied in the early 2000s for dense WDM applications, and I personally think it's something that hasn't sufficiently been exploited for higher power uniform supercontinuum generation in different wavelength ranges. So perhaps this is something to look at in the future as well. The reason we model supercontinuum generation and discuss its different physical effects is because we want to understand experiment. So if we look, for example, on the right, where we show an experimental output spectrum after 15 centimeters in a photonic crystal fiber with dispersion characteristics and structure shown to the left, we see it's quite complex, spanning from say 500 to 1400 nanometers with a complex series of peaks and valleys. If we simulate the same nonlinear propagation process, we obtain a spectrum that looks extremely similar. It has peaks and valleys as well. But what does this actually mean? Well, to understand that, we can plot the dynamics, the evolution of the temporal and spectral properties as a function of distance, and this is shown on the left. Instead of a black and white plot, this is perhaps better seen in terms of a false color plot. And here we can really start to see the physics revealed to us in a much clearer way, and we're able to see in particular the emergence of discrete time domain localized solitons, a broad background which we can associate with a dispersive wave, the initial point of soliton breakup or soliton fission that starts all this process where the periodic behavior of a higher order soliton is lost. In the frequency domain, we see the appearance of a dispersive wave on the blue side, on the short wavelength side of the spectrum, and we see also the continuous self-frequency shift of Raman solitons as they move to longer wavelengths. We can also extend the modelling beyond the femtosecond regime to study the physics of long pulse supercontinuum generation, such as 20 picosecond pulses shown here, injected into 2 meters of fibre. And we can also scan the input pump wavelength to see how that changes the dynamics. These results show a very rich variety of behavior. At 700 nanometers in the normal dispersion regime, the dynamics are essentially dominated by spontaneous Raman sidebands which eventually merge together and form a continuum. In the anomalous dispersion regime around 900 nanometers or around the zero dispersion wavelength itself, we see more clearly soliton dynamics with an initial phase of noise-driven spectral broadening, spontaneous modulation instability, ultimately leading to discrete solitons on the long wavelength edge. Now for longer pulses, such as these results shown here, a big difference with the femtosecond pulse case is that this is a very incoherent means of generating broadband light, and that if a pulsed source is used, these dynamics will vary from shot to shot in a very significant way, as we'll discuss later. The physics of supercontinuum dynamics in solid core fibre is well known by now, and recent research in this area focuses more on applying these results to generate supercontinua over broader bandwidths and in new wavelength ranges. So for example, we see on the left results using chalcodonide step index fibre to generate results into the far into the infrared, and the results on the right using a Z-band photonic crystal fibre are focusing more on extending both to short wavelengths in the ultraviolet as well as into the infrared. Many proof of principle supercontinuum experiments use OPOs as their pump source for tunability convenience. But with the development of new ultrafast fibre lasers in the infrared, it's possible to consider all fibre systems, and a nice example of this is shown here from Macquarie University, where a 2.9 micron fibre laser pump is used to generate a continuum in a chalcodonide taper spanning from 1.8 to 9.5 microns. And using even more common primary pump lasers around 1550 nanometers, if we have a clear understanding of the dynamics, it's possible to cascade supercontinuum generation in different types of fibre to access new spectral regions. These results, for example, published just last week, showed spectral broadening from a 1550 nanometer pump in 2 stages. First in Z-band fibre, and then if we filter part of the Z-band spectrum to pump a second segment of chalcodonide fibre, we're able ultimately to generate radiation over a 2 to 10 micron spectral range. And as well as these results studying supercontinuum and various combinations of glass fibre, there's been remarkable work combining silica and silicon, using silicon core fibres as a platform to study nonlinear effects. These papers, combining research from the ORC, Clemson and NTNU, provide an overview of work in this field, and the results on the right show the generation of a 2-octave span supercontinuum using 3 micron pumping from an OPO. Having a clear understanding of the dynamics also allows you to explore other ways to modify and optimize the supercontinuum for particular applications. This work from Benjamin Wetzel and others in Roberto Morandotti's group is especially exciting. Here, spectra are being generated in germanium-doped highly nonlinear fibre, but the initial conditions are being actively shaped to control soliton interactions in a particular way to target features such as enhanced spectral density and specific wavelength regimes. A genetic algorithm is used here in one of the first examples of these powerful machine learning techniques and experiments, and this is something which will clearly be an important area of work in the future. So far we've considered propagation in solid core fibre, but work in hollow core fibre has been equally influential and significant. In the early studies of nonlinear propagation in hollow core fibre, the interest was to exploit the low nonlinearity of air to propagate solitons at high power. But more recently, I think the real long-term application of this field has become apparent through the manipulation of nonlinearity and dispersion using different gas species in the fibre core. This allows you to tailor the soliton dynamics in specific ways and also study more complex plasma-related nonlinearities. This field has been pioneered at MPL in Erlangen, and this 2014 review already highlights its potential. And this slide shows some recent results in this area from John Travers at Heriot-Watt, using hollow capillary fibres to report soliton dynamics and pressure tunable dispersive wave generation in the ultraviolet down to around 100 nanometers and with energies at the microjoule level. Moreover, polarization gating frog measurements of the higher order soliton compression associated with this propagation has revealed intensity forwards at half maxima of around 1.2 femtoseconds. On the bottom right, the orange curve here shows the experimentally retrieved intensity envelope, modulating reconstructed intensity cycle oscillations underneath. Now these are remarkable results, and I'd like to stress again that the only reason these are possible is because they're preceded by a detailed process of modeling and interpretation of the soliton physics. At Clio this year, you can find online a number of papers on this particular topic, and I'd really encourage you to look at these for more detail and more information. And while we're talking about hollow core fibre, I'd like to highlight this work from Mariusz Klimczak on extending the novel anti-resonant hollow core design into the mid-infrared. Now this is at an early stage, but it's very promising, showing broad transmission windows over 500 nanometers and low bend loss. It's potentially a very important result for future studies of fibre-based mid-infrared spectroscopy. Moving away from fibre to planar waveguide platforms, the supercontinuum and nonlinear spectral broadening physics is similar to that in fibre, although other nonlinear absorption mechanisms may need to be considered in detail. But otherwise, the key concept of matching a particular pump wavelength to some particular dispersion engineering is central to obtaining a supercontinuum with desired characteristics. This is a very nice result from EPFL showing a waveguide design where a region of anomalous dispersion is situated between two regions of normal dispersion so that we can get two dispersive waves generated. The experimental spectra resulting is shown on the right. An overview of the broader field of photonic chip-based frequency combs was also provided in the 2019 review article referenced in the bottom, and this is worth a read to obtain an overview of the field. Many other materials have of course been explored for chip-based supercontinuum generation, including lithium niobate pumped at 50 nanometers. Now this is recent work from ETH pumping lithium niobate around 1 micron. And this is interesting because it allows you to obtain higher spectral densities at shorter wavelengths, extending into the visible, combining continuous spectral broadening through self-phase modulation and soliton effects with second harmonic generation occurring at the second harmonic of the pump. And while we're talking about chip-based and integrated supercontinuum and frequency comb sources, it's essential to distinguish the different physics between a waveguide pumped by a mode-locked laser and a microresonator pumped by a continuous wave. In the former case, a supercontinuum-based comb arises from essentially the same soliton dynamics as is observed in an optical fibre. In the second case, the frequency comb generation arises from parametric frequency conversion and the generation of cascaded four-wave mixing sidebands. There are both similarities and differences between the two systems in terms of detailed soliton dynamics, but they're not the same thing, and this needs to be borne in mind. The two review papers shown at the top provide excellent overviews of the ways to contrast and compare the two cases. So far, all the fibre nonlinear optics I've discussed has been single mode or near single mode, but it has to be stressed that the study of multi-mode nonlinear effects is extremely active. There are extremely interesting theoretical developments applying thermodynamic concepts to multi-mode systems, and there is enormous potential for the development of new high-power optical sources. These two papers provide an excellent overview, and those of you interested are strongly recommended to look at them both. Now, so far we haven't spoken much about the stability of the supercontinuum, but this is clearly something that's very important. Now, the interesting thing here is that even after the very first results in 1999, it became clear that depending on the particular experimental conditions, some supercontinua were stable and suitable for frequency metrology and others weren't. And something strange was going on in that often it was the smoother spectra, those that were more uniform spectrally, which were unsuitable, while the more structured spectra were those that were suitable for frequency metrology and exhibited lower noise. So something was going on, but it was unclear exactly what. It was here that simulations allowed this to be understood readily in terms of the extreme sensitivity to noise of the nonlinear dynamics of the supercontinuum spectral broadening. The simulation results on the left, for example, show 5 supercontinuum spectra generated in fibre under identical conditions aside from different random noise at the quantum 1 photon per mode level. Now, these 5 spectra can be considered as equivalent to 5 supercontinua generated from successive pulses from the laser. We see dramatic variations in structure from shot to shot, even though what you may measure using an integrating optical spectrum analyzer shown on the bottom could be artificially smooth. Now, the precise reason for the shot-to-shot variation can be complex, and for short pulses can include intrinsic sensitivity of higher order soliton propagation to noise, or more commonly, for longer picosecond pulses, as shown on the right, competition between coherent spectral broadening around the pump and incoherent modulation instability sidebands growing from noise outside the pump bandwidth. Now, there are guidelines available now to control these instabilities, such as keeping the soliton order of the input pulses around 10 or lower for anomalous dispersion regime pumping, or even avoiding soliton instabilities altogether by pumping in the normal dispersion regime. Although pumping in the normal dispersion regime generally requires higher peak powers to obtain the same bandwidth, this is an extremely active area of research, especially for applications in OCT and K spectroscopy. But even in the normal dispersion regime at high powers, new sources of noise are being uncovered. So current work is focusing on how to reduce this, how to quantify it, how to measure it. There are a number of papers here from DTU and NKT and ourselves, plus from Tampere, on exploring different ways to generate low noise supercontinuum in the normal dispersion regime. And if this is a field of interest, I'd encourage you to view these presentations. Before 2007, however, these supercontinuum spectral fluctuations had only been predicted numerically, and they'd never been measured on a shot-to-shot basis. But work by Daniel Solly and Bahram Jalali's group used real-time spectral characterization to directly record these shot-to-shot fluctuations on the long wavelength edge of a supercontinuum spectrum. Now, they went a lot further than this by noticing that the corresponding statistics were highly asymmetric with a long tail. They proposed a link between nonlinear fibre propagation and supercontinuum generation and the nonlinear wave shaping mechanisms on the ocean that cause giant destructive rogue waves. Now, this was an inspirational idea and has led to 13 years of work since, using optical systems to probe many different aspects of oceanographic wave shaping and attempt to pin down the physics of rogue waves in general. I've been lucky enough to work on a number of collaborations in this area, and a comprehensive review of the current state of the art is given in this recent paper from late last year. These results also stimulated interest in using real-time measurements more generally in nonlinear optics, and with techniques such as the dispersive Fourier transform, DFT, or the time lens magnifier, it's possible to obtain real-time characterization with sub-nanometer spectral and hundreds of femtoseconds temporal resolution. This slide outlines the principles. On the left we see the DFT, based on the fact that the temporal intensity of a pulse stretched by large linear dispersion is proportional to its spectral intensity. So when a picosecond pulse is dispersively stretched to a few nanoseconds, the stretched nanosecond profile is proportional to its spectrum. Since nanosecond timescales fall within the bandwidth of gigahertz detectors, this can be measured in real time. On the right, in the time domain, the time lens is shown as analogous to a standard spatial lens imaging system, but we replace diffraction by dispersion and we apply a quadratic temporal phase to mimic the spatial phase shift across a lens. In practice, this phase shift is applied through wavelength conversion, four-wave mixing, between a linearly chirped pulse and the signal under test, and magnifications of typically around 100 can be achieved, bringing picosecond pulses once again into the gigahertz regime where they can be detected. One of the first applications of the time lens technique in nonlinear fibre optics was to measure continuous wave modulation instability. Modulation instability on a high power continuous wave in a fibre typically generates random picosecond scale temporal peaks. And in these experiments we were able to use a time lens to magnify these to a nanosecond scale so we could measure their statistics and profiles to study particular connections with rogue waves. We were also able to show that at higher amplitudes the real-time fluctuating profiles tended to group around the theoretical peregrine soliton structure that I mentioned earlier. A limitation of the time lens is that the technology to implement it is not readily available at all wavelengths, but we've recently shown that machine learning can allow you to reliably infer time domain information even if all you have available is real-time DFT spectral characterization. The problem that you're trying to solve is shown here. Suppose that you study modulation instability in a system that produces shot-to-shot variations in frequency and in time for some input. Now, based on only the complex spectra that you measure, is there a way to infer information about the corresponding temporal field, and particularly in the context of rogue wave studies, can you infer the temporal intensity peaks? Now, the answer to this question is yes, and it's based on the power of a neural network to act as what's called a universal function approximator. Now, for those for whom this idea is unfamiliar, a neural network here is simply an algorithm written in MATLAB or Python or some other language that describes a series of mathematical steps, taking an input spectrum and then through linear and nonlinear operations and a number of discrete steps or layers using the machine learning jargon, calculates an output, which in this case would be one number. So we're trying somehow to construct or correlate from the complex modulation in the spectrum across all wavelengths, one simple number via a mapping to predict the corresponding temporal peak intensity. The details are given in this paper, and to cut a long story short, the basic result is that this works. You first use simulations to train the network to determine the transfer function linking the complex spectrum to the peak of the temporal profile. And then when you apply this to experimental data, you obtain a histogram of peak intensities, which is shown as the dashed red line in the figure. And this is in excellent agreement with NLSE simulations of the MI process and the fibre under study. There are some two papers in Clio on this that you can watch online, and there's also a recent paper on arXiv. Now, at the very start of this talk, I mentioned that this year is the 60th anniversary of the laser. And it was only a few years after the initial 1960 experiments that the first evidence of mode locking in lasers was seen. Now, in some cases, lasers don't exploit nonlinear interspersive effects, but in the majority of ultrafast lasers, they do. Indeed, most ultrafast lasers involve a soliton-like balance between self-phase modulation and group velocity dispersion. And in fact, one of the key reasons behind the rapid development of the ultrafast laser field in the 1980s was precisely because much of the theory from the fibre waveguide sector could be transferred into optimizing laser designs. In fact, the realization that there are so many common features between solitons and waveguides and in lasers has led to the generalization of the soliton concept to encompass not only a balance between nonlinearity and dispersion, but also gain and loss, creating the notion of a dissipative soliton whose existence can occur over a much wider range of parameters than might be expected based on a consideration of only nonlinear dispersive balance. And whilst laser dynamics is itself a very mature field, the particular application of dissipative soliton ideas to understand laser dynamics has exploded in the last 5 years, especially with the use of real-time measurement techniques to directly characterize laser instabilities. This is just a selection of the results that have been obtained, and it's worth noting that just in the last 18 months, more than 150 papers have appeared just on this area of instability characterization. As one example, these are results from 2018 that were performed in our labs in collaboration with Tampere, combining time lens and DFT measurements simultaneously to measure startup dynamics in a fiber laser. Now, these results were also interesting because not only were we able to measure the growth from noise of localized soliton structures, but because we simultaneously measured intensity in time and frequency, we were able to use phase retrieval to extract intensity in phase on a real-time basis as well. At this point, I'd just like to remark that real-time access to the full field of pulses from the laser or other forms of propagation opens up the possibility to extract the soliton eigenvalue content through the nonlinear Fourier transform. Now, this idea was proposed many years ago, but it's been seriously reanalyzed not only to obtain new insights into lasers, but also for transmission application. Now, although very familiar to applied mathematicians, these concepts are unfamiliar generally to photonics engineers. But this is definitely an area to watch in the future, and there are some nice articles starting to appear making this field accessible. It has to be admitted, though, that real-time full field characterization is still not routine, And the most widespread technique for characterizing laser instabilities remains the DFT because it's extremely simple to put into place. Now these are recent results from our lab, for example, characterizing instabilities in the dissipative soliton similariton laser. And with simple adjustments in the saturable absorber settings, we see a remarkable range of different effects. Now, on the right, we see both the spectral evolution over more than 4,000 round trips, and you can see a wide range of different structures appearing, from explosions to stable molecules to unstable molecules, and you can even get insight into the corresponding time domain information through a numerical Fourier transform of the spectrum, if the spectral resolution is good enough to allow you to see fringes because of constituent molecules. And these results really appear to be very generic features of the dissipative soliton balance between gain loss and NLSE dynamics. We recently reported a simple numerical model of this laser that, despite being developed in a scalar approximation and using very generic models for gain and saturable absorption, was able to reproduce essentially all the features that we saw in experiments. And finally, in this discussion of DFT and lasers, I'd like to highlight recent work from the group of Maria Czernysheva at the Leibniz Institute and with Aston, applying DFT to study ultrafast bidirectional lasers. Now, some of the first ultrafast lasers, such as the colliding pulse mode-locked dye laser, were bidirectional, but this design has largely been abandoned, and I think it's wonderful that some of these older ideas are now being revisited for new applications. And one application in particular has been the use of the DFT for Sagnac visualization, as shown in this paper that just appeared this year. So I'd encourage you to look at this work. It's very interesting. This tutorial has lasted an hour, but we've really only scratched the surface. However, there are many excellent review articles available and textbooks that will allow you to complete some of the details that I've only glossed over. From my own perspective, I'm extremely excited about this field. New measurement techniques and new methods of analysis are giving us new opportunities to understand and exploit nonlinear dynamics. And the nonlinear waveguide platform allows us to develop not only important applications and devices, but also to study wider areas of nonlinear physics, such as soliton localization and instabilities. So thank you very much for your attention, and please look at the references that I've referred to if you want more information, or please just contact me directly. Thank you very much.